Introduction to Semiconductor Materials, a presentation of eSys.org, prepared by Louis E. Frenzel. The prerequisites to understand this presentation, you should have the following prior knowledge. Draw the structure of an atom, including electrons, protons, and neutrons. Define resistance and conductance. Label an electronic schematic indicating current flow. Define Ohm's and Kirchhoff's laws. Describe the characteristics of DC and AC sine wave voltages. Student learning outcomes. Upon completion of viewing this presentation, you should be able to define conductor, insulator, and semiconductor and state the resistance or conductance of each. Name at least 3 semiconductor materials and state the most widely used. Name the basic structure of material and explain how it is formed with atoms. Define doping and name of the 2 types of semiconductor materials formed with doping. Name the current carriers in N and P type material. Explain how current flows in semiconductor material. Electronic materials. The goal of electronic materials is to generate and control the flow of an electrical current. Electronic materials include, first, conductors, materials that have low resistance which allows electrical current flow. Second, insulators, materials that have high resistance which suppresses electrical flow. And third, semiconductors, materials which can allow or suppress electrical current flow. Coming to the first category, conductors. Good conductors have low resistance, so electrons flow through them with ease. Examples of best conductors in the element form are copper, silver, gold, aluminum, and nickel. Alloys are also good conductors like brass and steel. Good conductors can also be liquid like salt water. Conductor atomic structure. The atomic structure of good conductors include only one electron in their outer shell. It is called a valence electron. It is easily stripped from the atom, producing current flow. Insulators have a high resistance, so current does not flow in them. Good insulators include glass, ceramic, plastics, and wood. Most insulators are compounds of several elements. The atoms are tightly bound to one another, so electrons are difficult to strip away for current flow. Coming to the third category, semiconductors. Semiconductors are materials that essentially can be conditioned to act as good conductors or good insulators or anything in between. Common elements such as carbon, silicon, and germanium are semiconductors. Silicon is the best and most widely used semiconductor. Semiconductor valence orbit. The main characteristic of a semiconductor element is that it has 4 electrons in its outer or valence orbit, as shown in the figure. Crystal lattice structure. The unique capability of semiconductor atoms is their ability to link together to form a physical structure called a crystal lattice. The atoms link together with one another, sharing their outer electrons. These links are called covalent bonds. The diagram shows a 3D crystal lattice structure showing the silicon atoms in pink color placed at the corners or face of an imaginary cube, and the links shown as dark lines connecting the atoms are covalent bonds. Semiconductors can be insulators. If the material is pure semiconductor material like silicon, the crystal lattice structure forms an excellent insulator since all the atoms are bound to one another and are not free for current flow. Good insulating semiconductor material is referred to as intrinsic. Since the outer valence electrons of each atom are tightly bound together with one another, the electrons are difficult to dislodge for current flow. Silicon in this form is a great insulator. Semiconductor material is often used as an insulator. Now coming to the concept of doping. To make the semiconductor conduct electricity, other atoms like impurities must be added. What are impurities? Impurities are different elements. This process of adding impurities to pure semiconductors is called doping. Semiconductors can be conductors. An impurity or element like arsenic has 5 valence electrons. Adding arsenic will allow 4 of the arsenic valence electrons to bond with the neighboring silicon atoms. The 1 electron left over for each arsenic atom becomes available to conduct current flow. Resistance effects of doping. If you use lots of arsenic atoms for doping, there will be lots of extra electrons, so the resistance of the material will be low and current will flow freely. If you use only a few arsenic atoms, there will be fewer free electrons, so the resistance will be high and less current will flow. By controlling the doping amount, virtually any resistance can be achieved. Another way to dope: you can also dope a semiconductor material with an atom, such as boron, that has only 3 valence electrons. The 3 electrons in the outer orbit do form covalent bonds with its neighboring semiconductor atoms as before, but 1 electron is missing from the bond. This place where a 4th electron should be is referred to as a hole. The hole assumes a positive charge, so it can attract electrons from some other source. Holes become a type of current carrier like the electron to support current flow. Types of semiconductor material. The silicon doped with extra electrons is called an n-type semiconductor. N is for negative, which is the charge of an electron. Silicon doped with material missing electrons that produce locations called holes is called p-type semiconductor. P is for positive, which is the charge of a hole. Current flow in n-type semiconductors. The DC voltage source has a positive terminal that attracts the free electrons in the semiconductor and pulls them away from their atoms, leaving the atoms charged positively. Electrons from the negative terminal of the supply enter the semiconductor material and are attracted by the positive charge of the atoms, missing one of their electrons. Current flows from the positive terminal to the negative terminal. Current flow in p-type semiconductors. Electrons from the negative supply terminal are attracted to the positive holes and fill them. The positive terminal of the supply pulls the electrons from the holes, leaving the holes to attract more electrons. Current flows from the negative terminal to the positive terminal in terms of charge carriers. Inside the semiconductor, current flow is actually by the movement of the holes from positive to negative. Hence, the current finally flows from positive terminal to the negative terminal as per the conventions of current flow. In summary, it is the semiconductor material in its pure state an excellent insulator. The commonly used semiconductor material is silicon. Semiconductor materials can be doped with other atoms to add or subtract electrons. An n-type semiconductor material has extra electrons. A p-type semiconductor material has a shortage of electrons with vacancies called holes. The heavier the doping, the greater the conductivity and the lower the resistance. By controlling the doping of silicon, the semiconductor material can be made as conductive as desired. Thank you.